This is the button code everyone writes. It works, it's clean, and it completely falls apart the moment your project grows. So today we're doing the Universal Button Library Part 2, which now also has double click and latch functionality. For the beginners, let's do a 3-part tutorial within Arduino, and for those who've been following the series, I'll show you how it scales within the Power Wheels project. Welcome to more Little Man Builds. So as always, let's search for the library we're working with today, which is called Universal Button. Once that's installed, we want to go to the example sketches. And let's firstly open Basic Button. So this is pretty much the hello world of buttons. And if you're new, this is the only button pattern you'll ever need. So at the top, we define the buttons once, or in this case, just one at compile time using a simple mapping. In this case, we've got a button called test button on pin number 6 using an input pull-up. The library uses that mapping to generate everything it needs internally. So there's no dynamic allocation and no runtime setup per button. In the loop, we call buttons.update, and that's where all the debounce and state tracking happens. Then we just ask a simple question: is the button pressed? There's no timing code here, no delays for debouncing, and no edge case logic in the loop. Just clean, readable intent. This is already better than most manual button code, and we're only scratching the surface. So let's send this sketch over to the ESP32. And let's open the serial monitor. And we'll bring in the camera. We have 4 buttons. This one's tied to pin 6, 7, 8, and 9. Each of them is grounded, so when they're pressed, we should trigger a button input. Currently, there's no input detected, but if we press the button on pin 6, we have test button is pressed. But most projects don't care that a button was pressed. They care how it was pressed. So here's the challenge. How can one button do 3 things while keeping the loop clean? So this is the second example sketch press type. At the top, the button mapping is exactly the same. 1 button, 1 pin. What changes is the timing. Here we define a timing profile: debounce time, how long a short press is, when a press becomes a long press, and how close 2 presses need to be to count as a double click. The timing gets passed inside the button handler once, up front, not scattered through the loop. Inside loop, we still just call update, but instead of polling a Boolean, we ask the button for an event. The library tells us whether this was a short press, a long press, or a double click, and it only reports each event once. Notice there's no timing logic, no state machines, and no edge detection here. All of that complexity lives inside the library. And this is the point where one physical button starts behaving like multiple controls. So let's bring in the serial monitor again. There's a short press, a double click, and if I hold it, a long press detected. Let's do each of those again. A short press, a double click, and a long press. Easy. So can we go one step further? Instead of asking, is the button pressed, we should ask, what just happened? So we've loaded up the third sketch, the local enumerator. This is where buttons stop being hardware and start being events. In the first 2 sketches, we used helpers to keep things simple. This sketch peels back the curtain a bit. Instead of a macro or a factory, the buttons are explicitly defined using a local enumerator. By the way, if you're enjoying today's content, smash the like button or please consider subscribing. It really helps me out with the algorithm and I'd love for you to join our community. Each enum value represents intent, not a pin number. We then map those enum values to GPIO pins in the simple array, and that's it. The button handler is templated on the number of buttons, so everything is still fixed at compile time. No dynamic allocation, no runtime guessing. In the loop, we're doing the same thing as before, calling update and asking for button state. The only difference is that we're now working with named inputs, not raw pin numbers, and this is exactly the pattern you want once a project grows past a single sketch. We don't care that test button 1 happens to be on pin number 6. We care that it's the horn or the indicator or the accelerator. The enumerators let us name intent and map the hardware later. By the way, we're still tracking press duration here, which just means high-level logic doesn't need to measure time itself. And so now we've got 2 buttons. I'm tracking how long test button 1 was pressed, or I've also got test button number 2. And there's the quick example of using buttons with enumerators. And once your inputs look like this, you're ready to plug them into a real control system. So let's take everything we just learned and put them into a real project. But we need something in the middle because buttons shouldn't directly control things, especially hardware. Everything in this project falls into one of 3 buckets: input, decision, and execution. And the biggest mistake people make is mixing these together. Let's start on the left. No logic, no behavior, just input. This is where the universal button library fits. It turns noisy hardware into clean, reliable events, and then it stops. No delays, no timing hacks. Now here's the important part. Buttons aren't the only input. RC input comes in here too. Different source, same philosophy. For now, the most important box in the system is the control core. This is where the decisions are made. Basically, who is allowed to do what. This is the single authority and decision maker for all output, whether it's motion, a sound, or an indicating light. Finally, we have execution, currently just the motor driver, but for the engineers, we could have also called this layer actuation. This layer doesn't care who asks for the movement, it only cares how to do it efficiently and safely, and for this, we use the MCPWM library. To move data through our system, we rely on buses and the snapshot bus library. These aren't queues, they're not messages, they're just truth, a clean, consistent snapshot of the world right now. And still, nothing reacts or moves at this point. Only once a decision is made is it published as an instruction via the control bus. This bus is the authority. Nothing downstream questions it, nothing upstream bypasses it. So when I add a new button, or a double click, or another input device, nothing breaks because each layer has exactly one job. And this is what the entire system looks like when you stop wiring buttons directly to behavior. Buttons and RC receivers shouldn't move motors. Only decisions should move motors. And it all starts here. By the way, there are other examples in the button library which include adding an I/O expander and latching, and these topics will be explored in the future. But if you missed any of our previous episodes on the above topics, I'll put a link to the playlist on the screen right now. So let's start off in our app config file, all the way down to the bottom. And just to show you how simply this system scales, let's add some more buttons. So the first one we're going to add is, using the same convention X, we'll add a horn. Now to conform with the convention, we do need to put these backslashes in. Let's save that and move on. So I'm actually going to rename this to input bus. So let's quickly fix everything here. What we should do is declare the instance of the input bus. So that file is now updated. We're going to add a new file today called control bus. So as always, I will do a copy and paste for the header. And now we need to create our struct, which is our snapshot or payload. By the way, if you're enjoying today's content, smash the like button or please consider subscribing. It really helps me out with the algorithm and I'd love for you to join our community. Next, let's create a type alias. Then we do the same as before. So in this case, the control bus is correct, but I think I made a mistake with the RC bus. And yeah, so we need to move this down. So the mistake I've made is that in C++, templates are built immediately. So the snapshot type has to exist before we create the bus. The compiler won't guess what the payload looks like after. So the bus needs to be built from the snapshot. So the snapshot has to be defined first. So basically I should move this below this code and we'll put it here, which makes more sense. I don't know what's generating this error, this MIT license. It's obviously wrong. So there's our control bus finished. The next file we should update is our state manager. So here we have to say input bus. Everything here is the same. So now we no longer need to attach the RC bus. And of course, this also means that we can get rid of the demo read section. Let's update the state manager.cpp as well. And then we can completely eliminate this block of code. We now need to introduce our control core. Let's create a new folder. Copy and paste of our header file. So we have our class control core, a default constructor. So we construct our input bus and output bus. And we will also use our task trampoline architecture. We need our main run loop. And then we're going to need some button roles. So a policy level. For simplicity and readability, we're just redefining the buttons locally within the file, but of course using our button index to actually figure out what number or pin number it was. So I can do this for all our buttons. The reason I'm doing this is to make sure that everything is clamped properly. So we don't expect values outside of what we're defining here. As always, we have our internal state variables. So we have the input bus coming in, we have the control bus going out, and so these are just declared as pointers. And we have our loop ticks, which controls how quickly our loop runs. Lastly, we also want to declare an input state previous. And this is true once prev is valid. And I'll explain a little bit more on this later. So first of all, we have to do a config assert. And then we need our run loop. So the first thing is input state current. We want to peek at the value. Then we want to do some input event logging. Next, we're going to build control commands. What will we say? Out throttle command %. If the button is pushed, it's going to be max %, and if it's not pushed, it's going to output min %. Then we need our out indicator command. What else do we need to send out? We need our timestamp, which is equal to current.stamp milliseconds. And then to send out our payload, we say out and publish. Then we're going to update the previous snapshot for next edge detection. Just to quickly go back on this has previous and previous. Has previous prevents false edge detection in undefined behavior on startup. So we explicitly mark when a previous snapshot becomes valid. If we initialize this up front, say to 0, the system would think that buttons were pressed at boot. So we only mark it valid after the first real read. So there's our control core framework, which roughly follows everything that we've done so far. And if you missed the snapshot bus library episode, I'll put a link to that in the corner right now. So let's close those two. Next, we have our power drive handler to update. We need to update here to control bus. We don't need buttons any further. And then we need an internal state. So we still have our iMotor driver. We then need our control bus, tick type, and float current percent are all the same. Firstly is to create a control snapshot. Then we need a target selection. And we'll do a cheeky way of clamping. Then we have simple acceleration, deceleration, which we will say is rate based. This uses our loop ticks and the port tick period microsecond divided by 1,000 to create a rate-based acceleration and deceleration. Const float, we say ramp step percent. Keep this commented out for now, just so you can see what's happening when buttons are pressed, and after that we can show how when a button is pressed, the state of the motor changes. And then we still have our pace loop. And I honestly don't know what I'm smoking because this shouldn't be here at all. Apologies for that mistake. So now we can close these two files. And so lastly, we then need to update our main.cpp. So we have our constants and type definitions. We did add another task trampoline. Let's go through and update all these to include that now. And drive motor is obviously not taking input bus. It should be taking control bus. We do not need to attach the consumers any further. And we can add another task. Let's save that and see if it compiles. First time's a charm. So let's send it over to the ESP32 and give it a test. So when I press each of my buttons, it gives me my pressed and released. Gives me my horn pressed and released timestamp, my indicator left pressed and released, and my indicator right pressed and released. And you may remember that we built in our utilities this function here called log button events. And so that's where that is coming from. So this was part of our input bus. So all our buttons seem to be working really well. I can click them together. There's no real issue. I can pretty much I can press one and then another one release, and then it will still track everything at the same time. And that seems to be working really well. Next, we need to go back into our drive handler, and we will uncomment this section here. Same. We will go to our control core, and we don't want to log the button events. So now when I re-upload this sketch, we are looking at the speed, and then as I press it, I can increase the motor's speed, and as I let it go, it decreases again. And all the other buttons obviously don't display because I don't have that code running at the same time. It's just literally too much for the serial monitor. But I hope that gives you a quick overview of how we integrate buttons at a project level. And with the snapshot bus library coupled with the universal button library, it just makes everything cleaner and far more efficient. Today, we started with the simplest possible button and ended up with a system that scales. More importantly, we separated input from decision. So if in the future we add double clicks, latching, or even new devices, nothing will break. Of course, everything that we did today you can find on our GitHub page, link in the description. Please also consider subscribing and smash that like button. See you in the next one.